Okay, so I guess let's get started. So we'll come back to EE631. So we post homework 1, and then you will be due in about 2 weeks. So you should have a lot of fun playing with the signal processing method, and also method. Okay, any question? Okay, so let's continue on the technology. So today we will start to look into this so-called variability. And definition of variability is basically anything that is not a nominal value. Okay, nominal value can be whatever your transistor width, length, or resistor value, right? So those are nominal values that we intend to design. But in reality, all this technology will always give you some deviation, right? And there are so many different mechanisms that will cause the deviation. So we're just gonna kind of go through all this one by one. Okay. So remember last time I talked about some of the variation can vary over time. Some will be more or less constant. Okay, when you get the chip back. Okay, so so if that's something that will not really vary over time, we call that as a static. Okay, so what that means is that once you get your chip back from the foundry, right? So this is time invariant. So it will not change. Okay, so there's nothing that you put the chip over there, even put it for 10 years, they will remain the same. They will remain the same. Okay, so the common mechanism for this, as you can see, you can probably guess, is related to how the foundry produce your chip. Okay, so when TSMC or Global Foundry, right, or Samsung Fab or Intel Fab, right, when they are manufacturing all this, the process engineer, when they do that in the fab, it's already there. Okay, it's not like, okay, you bring the chip back and say, oh, by the way, let me dope a little bit more with the particle. That's just impossible, right? So that'll be fixed. And to capture those effects, usually we do that in the process corner. We call that the process corners. So usually we will categorize that into different kind of category. So there will be slow, there will be fast, there will be typical, right? So those are the terminology that you're gonna see. So is that a slow corner, is that a fast corner, is that a typical corner? Okay, so that's usually how the foundry will help us to define the boundary. Okay, so usually this will be provided by the model. Okay, so when you are going to use a TSMC or Global Foundry particular process, if you download the so-called PDK, basically those will describe all the devices that you're going to use based on their function. All right. And anything that related to the manufacture of your chip, right, or wafer, right? So like lithography, line edge roughness. So this is how they, deposit like a metal line, right? When they deposit metal line, it won't be perfect, right? You say, okay, yeah, give me this rectangular shape. But if you look at edge, it'll be jiggly, okay, right? It won't be, by and large, you look like, oh, that's perfect surface, but it won't be, right? So it's always some roughness over there. Doping, right? So the process, use a lot of doping to control certain property. For example, the threshold voltage. Okay, so that's certainly, related to how the process do the doping. There will be also WP effects, TI stress. I will talk about those, so don't worry about that. So basically, still related to the structure of your the manufacture of your device. Okay. On the bottom, those are the typical techniques that we as designers we need to mitigate. Okay, if you have a static errors, usually you need to leave for a margin. So that's what we call the design margin. All right. So when you design, so let's say if you are shooting for a certain speed, guess what? So your device can be slow, can be fast, can be typical. So what corner should I really watch out for? Slow corner, right? If there's a certain speed you want to hit, you got to make sure that even at the slow corner, you still meet that speed requirement, right? As an example. So that is what we call the design margin, right? Not always, you should only consider the slow corner, right? So for example, sometimes the leakage, if the leakage is one of the big concern, usually we need to check the fast corner. Right, because typically the fast corner is more leaky, right? So there are just so many different design considerations that you need to be careful, right? And by and large, those are called design margin.
How much of these are accounted by like the various DRC rules?
Okay. Okay, so you are jumping a little bit ahead. So there is something called DRC rules. So for those of you who have done layout before, this is after you complete your layout, you need to make sure you follow the foundry guideline. For instance, you say, okay, I have two wires next to each other, right? Can I just make it arbitrarily close? You can imagine you cannot, right? So that's called DRC rule, right? So when you run the DRC rule, all they check is just, oh, are you following our guideline? Okay, I told you need to leave at least 5 nanometer, for example. Why do you make it 1 nanometer, right? So they will flag. So that's DRC rules. Those DRC rules, they don't capture different process corner, because all they check is just that are you following our guideline? Okay, our guide. If you violate our guide, I'm sorry, I'm not gonna let you tape out. A lot of times they do this now. The question you may wonder is, hey, you know what? That's your fault. You didn't follow us. It's your fault. So why do the foundry care? It turns out that, so later on we'll talk about this, right? So if let's say someone next to you totally screw up the layout, unfortunately it will also affect the circuit next to you. Okay, so it's no longer your problem. Okay, is just stay with your problem. It's not like go to Vegas, everything happens, just stay there. So now it will start to spill out, right? It will spill out and it will screw up your neighbors, right? So for that reason, generally speaking, the foundry, they do not allow you to do this violation. Okay. All right, another common technique to do this is so-called calibration, right? So there will be some calibration techniques that usually people do, right? So for example, if you are too slow, someone's, if let's say your circuit's speed depends on the bias current, right? Then maybe they can have some tuning mechanism on the current, just so that, if you're unlucky, you go to the slow corner, maybe I can increase the current to compensate. Yeah. So that's what we call as a calibration. By the way, that calibration technique is very common. So you're gonna realize that this calibration is very, very common. In fact, a lot of times people even do this sensor to sense that I'm in the slow corner or fast corner or typical corner. Okay, so there will be some kind of process corner sensors, building, right? So if you know that you're slow, all right. So what do you want to do with your circuits? right? So that's where you can come in, because you understand the circuit, you design your own circuit, so hopefully you will understand how you can mitigate those impacts. Okay, so those are the static. Unfortunately, there are also a lot of mechanisms that will change over time. Okay, and they are at different scale, right? So some of the change will change over seconds. Okay, including, for example, power supply. Then you look at this and say, okay, why would my power supply change? If you say, okay, this is a 5 volt, 4 volts, right? Like your battery, AA battery, would the voltage change?
Depends on your circuit, like how much current you are.
Yeah, so
requesting
let's say
from-
you follow the rule, right? So it's all within the whatever the battery can supply the current. So it turns out that from between the different battery, maybe there's a little bit of differences, right? And more importantly, because it's over time. As your battery about to run out, have you guys had that experience? The battery is about to run out, and then you think that your device doesn't really function as well, right? And a lot of times that's really because your voltage actually is dropping. If this is a 5 volt battery, right? Just about you're about to run out, this 5 volt can gradually degrade to 4 volt, and then 4 volt, everything dies, you should go down. Okay, so those can change by seconds, right? So it won't be happening like right away, right? So, but over seconds or minutes or hours, you can see that it's going to change. Another thing that you can change, like temperature, right? Temperature can change, over on these scales. There are a bunch of aging effects, so I will talk about this later, right? Like hard carrier and BTI, drift. So this is what we call the aging effect. Okay, so what is aging? You use your device, right? We use every day. I use every day. Do you expect that this year I use this and next year I use this same device? Would that behave the same? It cannot. Even if you say, okay, Mike, I'm gonna replace my battery. Good luck. You replace your battery. That device is absolutely not the same as before. Okay. So because you keep doing that, there will be aging, just like pretty much any physical object, right? You look at mechanics, even the table, right? Chairs, you do over time, it changes. It has to change. So same as our electronic device. Okay, so over time, how that will change and how long it should last. Okay, that's really the problem that when you are going to do the circuit design, you got to figure that out first. Okay, right now in industry, guess how much time they are shooting for. So let's say I don't know, your laptop, your phone, guess what? How many years?
3 years, 4 years.
5.
Supposedly it should be 10 years. Do you actually use your device for 10 years? Yeah. So I heard, because all the customers now change their taste so fast, they start to shrink. Who cares about 10 years? Okay, let's just say 5 years or 3 years, right? But not always. Okay, some of the electronic component you got to really shoot for 10 years or even longer. Give me an example. What the electronics device that we need to shoot for?
Satellites.
Yeah, so biomedical device, right? So you like a pacemaker, you do that. You don't want to. Okay, let me open up your heart every year. Okay, time for maintenance. Okay, so that doesn't sound fun. Satellite, same thing, right? So think about how much. Actually, can satellite be brought back and then fixed? No, you cannot do that, right?
If they want to do it, they can. There probably is enough technology to achieve that. Like, I think it costs too much.
Yeah, I would think that they
You
probably.
won't go far, though. I haven't watched
Yeah,
the five.
they probably just I don't know, self-destroy, and then they fall on Earth or whatever, right? And then they just shoot another one up, right? That's probably faster. All right, so there will be applications where the lifetime is extremely critical, right? So the space application actually is coming. This is no joke. You know, LA is one of the big hub for the space electronics. Do you know which company? SpaceX. And let's don't forget, I know SpaceX and
Aerospace, like radio.
all the aerospace, exactly. By the way, LA is one of the big hub for all the defense industry, just in case you don't know. Next time, oh no, so don't try to break in, okay? But you know, if you go to LAX area, next time if you wander around that area, you look at the building, there's no sign, no mark, no nothing. Yeah, you know they might be doing something inside. It's just that you don't know, right? So I have the fortune to visit some of those companies. Some of the very extreme, you know, highly secured site. Even the window they block it. They have a window, they all block. It's so dark inside, so they have, of course, good lighting. But really, seriously, from outside, you have no idea what's going on, right? So a lot of those aerospace companies, they seriously care about all this. You know, we talk about aging, right? All these effects. Pretty much that's the number one thing they care about. It's very different from, let's say Apple. Okay, Apple or Samsung, they probably care about their next product, how fast they can run, how low power they can run. You know, those companies, they don't care. They just, okay, I just want this to be functional. By the way, for the next 50 years. So good luck with that. How do you do this, right? So you can see, as a circuit designer, you will have some different perspective in the future, right? So don't think that your only one goal is just do this, right? So the different aspect, you know, maybe more important than the other one. So my strategy is that, you know, we just understand everything. So in the future, you know, if your next project is, oh by the way, that's okay about the aging, okay, and then you know what you should look out for. All right, so those will be on the order of seconds or longer. Flicker noise you learn from 536A, right? So depending on what the flicker noise frequency, you know, this can be severe. Soft breakdown, yeah, this also a little bit related to aging effect. So all that, you know, oftentimes, you know, we may have some compensation circuits, okay, to actually compensate for those, so let's say aging effect or temperature drift. You know, in fact, you know, most of the product, especially if you care about the performance, they have something called the temperature sensor. In fact, I think most of your processor core, they have a temperature sensor. And right now, you know, there are multiple core, right? You know, I've seen where people do one sensor for one core. So if you have 100 cores, they have 100 sensors, just on the temperature. Okay, so based on the temperature, then it's, oh, okay, I got to do something to this core, okay, because it's too hot, or maybe it's too cold, then what do you do about it? Okay, so that's on the time scale on the seconds or more. Some of them will be on the microseconds, right? So for example, IR drop. So you build the circuits, right? You took a VLSI class, right? Most of you, right? Inverter. When would the inverter draw a lot of current? When you are switching, right? When you switch to one, the inverter pretty much nothing happens. But when you're switching, boop, it's like a lot of current, right? And if one inverter, probably you are okay. But imagine if you have a 1 million inverter, right? So good luck with that, right? So if imagine if you have 1 million or thousands of inverters taking the current, those current has to come from supply, right? So if your supply has this IR resistance, so we'll call the IR drop, right? So momentarily you will have a dip. I times R, that's the voltage, right? So you have a dip. So some of the circuits, you know, will see this short term, like microseconds. Actually, depends on how fast you tackle this, right? So right now, probably even nanosecond, because nanosecond corresponds to gigahertz, right? Because you may be, you know, toggling at the gigahertz rate. Some of the temperature gradient, which I will show you, can be also on the order of microseconds. Flicker noise, obviously, because it's depends on where your corner frequency is, so they can also get into this regime. All right, so usually, what you do is that you just further stretch your design margin, right? Because if you anticipate some additional IR drop, that means that circuit's better to work at an even lower voltage, as an example. All right, some of the things will be even faster, right? So it can be picosecond range, right? So dynamic IR drop, so some dynamic circuit, you just draw the current in a very short time. Jitter, right? So we the clock, the circuits, can come with the jitter. So when we talk about the sampling circuit, I'm gonna show you how that jitter impact. So the jitter can vary like picoseconds. Substrate noise, basically all the noise, coupling noise, right? So when other circuits are operating, you can affect the circuit that you're operating. So those can also be at the picosecond level. Thermal noise. Thermal noise, remember, is a white noise, right? So it can go all the way to very high frequency, right? So it can also vary at the picosecond range. So it will force you to enlarge your design margin even more. Okay, so there's really a lot of different defects, but as I mentioned last time, thanks to all these defects, we have a job, right? Otherwise, it's just math exercise. Okay, so here I'll give you one example. So this is called the negative bias temperature instability, NBTI. Basically what happens is that your threshold voltage will drift over time, okay? And in particular, this NBTI effect mostly affect the PMOS. Okay, so if you have a negative voltage, like this is PMOS, right? So to turn on this, your VGS is a negative voltage, right? Do you agree? Right, so whenever you have this, and then if you have this negative voltage, in order to operate this, your threshold voltage can change. So here's one measurement, right? So whenever so this is the time that you stress, right? Okay, over time, you will stress. So those are the different stress level that they will do. So you will see that it will drift, right? So this is a delta threshold voltage, right? So whatever that nominal value that you have to begin with, it will start to change. And then you see this dip right here, right? So in this particular stress test, so they will apply this VGS right here, right? Stress it, right? Stress, operate, and they will release. Once you release that VGS, guess what? The threshold voltage go back, right? So then the question is that then why do I care? So you stress, so long as you don't operate for too long, right? This always go back. This always go back, right? Go back. But unfortunately, only at a certain time scale, yeah, it will go back. You see this? If you actually do more, it will not go back to the original value. So you will start to actually have a long-term drift. Okay, so this NBTI, effect, if you look at the long term, by the way, this is over seconds, right? So you see, after 10,000 seconds, 10,000 seconds, you already see that even if you release the stress, it will not go back. Okay, so that means that you already have a permanent damage to your threshold voltage, right? So this device characteristics already change over time. So then the question is that you need to decide for your circuit that you're building, is that okay? It really depends. Okay, maybe in some cases you are really lucky, it's really okay. But in other scenario, maybe it is not okay, right? It maybe will affect, screw up your bias, for example, right? So, or affect your overall gain or stability, things like that. So those are the questions that you need to basically worry about. Okay, so that's NBTI. And there is another related effect called PBTI. and this is the opposite of the MBTI. MBTI is you apply the negative BGS, right? So that's why it's PMOS. So guess what? What is the PBTI? So that's positive BGS. So what device uses positive BGS? It's NMOS, right? So yeah. So there is an equivalent effect for the NMOS PBTI. But in general, the MBTI effect is more prominent than the PBTI. Okay. Hot carrier effect. So the hot carrier effect usually is when you have a high vertical or horizontal electric field. So let's say between the drain and source or gate bulk, you will speed up this carrier, right? So for NMOS, for example, is the electron, right? Electron is the carrier, right? PMOS, that's the hole, right? And when these carriers are flowing through the channel, some of them can get trapped in the gate oxide. Okay, and once you trap in the gate oxide, you will change your effective threshold voltage. Okay, so again, you change the threshold voltage of a device, and that usually is not very good, right? Because as you design the circuit, the threshold voltage really change everything, right? Change how you turn on, change your VD set, right? Remember VD set, right? The overdrive voltage, and then it changed the region of operation, right? And then your whole circuit behavior actually changes. Okay, so typically, whenever you have this aging effect or the stress effect, the higher the voltage will make it worse. Typically, right? So here you can see this example, right? So again, all these are coming from papers, research papers. You can see, for example, all this the circle one, right? So that's when they stress the VGS is 2.5 volt, and this is the VDS is 2.5 volt. Okay, so you have more drift, right? But then if you can see, so let's say between this diamond and triangle, right? So the triangle here, you see the VDS is 2.4 volt, right? So that's a bit higher than the diamond one, which is 2.2 volt, and you can clearly see that this curve shift, right? So it's just more delta VTH. So yeah, so that's a general guideline. So essentially, the more field, because the hot carrier is really depends on your horizontal and vertical field. So this VGS and VDS, will affect how much trapping will happen to your carrier. Okay. All right, so that's hot carrier effect. So those are the very dominant effect, especially onto aging. I think that's what people care the most, hot carrier and MBTI. There is also something related to the gate oxide breakdown. So there's a TTDP, for example, right? So they will look at how much your gate oxide will start to have a tunneling through. So yeah, so there are actually many different aging effects. So here I just give you the two most prominent ones, right? So, but it doesn't mean that they are the only one. Okay. Remember I told you about some of the electronic system, they care about the lifetime. There they do all kind of study. Okay, not only they have this theoretical study from the physics perspective, they even take out the test structures. The engineer just, they call it a stress test in the lab. So they do stress test test in the lab, and they have a model, right? In fact, the model is so sophisticated, right? Everybody know you cannot do the test for 50 years. We cannot, right? So what do you do then?
I heat the device up to...
Heat up? A little bit similar to that, right? So there will be like overstressed. So for example, right? So let's say a MBTI. You say, okay, yeah, typically I operate this, right? So let's say inverter, right? What's the largest BGS? VDD, right? And then you say, oh yeah, typically just VDD, and then typically when you operate the inverter, there's a certain time that you operate, sometimes you don't, right? So, but that doesn't give me a good sense of how, because I cannot wait for 50 years, right? So what do? They say, okay, I need to make it worse. How do I make it worse?
5 VDD.
So you can increase the VDD, right? So I would overstress it, right? And then I can always, bias this all the time, even though I know that this people sometimes will be off. So I don't let it off. I just continue to stress it, right? So this is they call it the shortened kind of highly stressed scenario where they can characterize. So let's say within 1 month, but the 1 month is possible. It's easily, you see the industry product, they will stress for the entire month. They send it in, they just wait. 1 month, take it out, measure again. Right? So you can do this, right? And you can have a breakpoint every week. I go there and measure it, and I see how this device gradually move. And what do? You predict. You just do extrapolation. Okay, so it's actually pretty fun. I think I know some of you are device people, right? So device people, they have all this physical model, and then they can predict, how long you're gonna survive, right?
Is there actual long-term study that measure what's the correspondence between the predict model and the actual?
I'm pretty sure that there are. Unfortunately, I'm not as familiar in that field, but I think in the there's an IEEE society. Okay, they really do the reliability study. In fact, I think they just call something reliability. Okay, and I think I actually attend a couple of their conference. It is pretty fun. Every talk I go there and everybody talk about, oh yeah, this is how I stress. Okay, yeah, and it is very creative, right? So I go there, I say, okay, no, I wouldn't even operate my circuit like that, right? But they, like I said, they have to fit in their physical model, so they would stress in a particular way or creative way, and that's how they publish paper. Yeah, so I wouldn't be surprised that somebody actually study all these long-term effects, right? In fact, some of the space mission, I believe that's what they do. So let's say I want to see how these circuits behave, right? So let's say I want to send it to Mars, right? I need to know how would this device or this transistor still behave. So they will send out to the space and circle the Earth, I don't know for how long. And when they come back, right, they say, okay, yeah, so now return the parts to me. I'm gonna measure again to see how that works. Yeah. So I know people, I'm pretty sure that that's some of the space mission, that's what they do. Of course, a lot of them are secret. You wouldn't know, I wouldn't know. So. Okay. All right. Some of the variations, so those variations are over time, right? So these are the sort of the time variability. Some of the variation is over the location. Location. Okay. So what do I mean by location? You know how our circuit was fabricated? Typically our circuit is what, millimeter or centimeter size, right? But TSMC today do this, put the transistor on each die. We call it a die. They don't, right? So instead, they put on the wafer. Have you guys seen the wafer? Probably maybe some of your undergrad class, you have this wafer, right? Right now it's how many inch? 16 inch? 13?
I don't know, diameter is I think 13 for digital.
Yeah, 12 inch for sure. What is the typical pizza size? 12 inch. Yeah, I like to think about the wafer as a pizza. So basically just like that. And of course that's all the foundry secret, right? So they take the pizza and then just process those pizza all over the place, different steps. Right now, of course, you know, we have all the robotics, so a lot of this manufacturing process, you know, are replaced by robotics. But in the old days, really human. So you have a human to go there, load, take out, do all the shift. I hope none of you actually have experienced that. You did?
I did in the lab.
Oh, you did in the lab. Okay. Yeah. So, yeah, from what I heard, it's very intense. A lot of people cannot sustain the process, right? So, okay. So they do all the hard works, right? And they do they manufacture the entire pizza, right? And you see all this grid right here. So those are your die, right? So you do this chip. So that's why you send them something called reticle, right? So your design, that's where you do the DRC checks. You say, okay, fine, and they will do duplicate, right? So duplicate through the entire pizza, wafer, yeah. And once the wafer is done, and how do they give the die to you? They will cut it, they will slice it, so they give you, so that's what we know as a chip, a bare die. And once you get the bare die, of course, then you come back and do the packaging. Okay, so yeah, so that's how it works. All right, so as you can imagine, you know, when TSMC or Samsung, right, Global Foundry, when they manufacture the entire wafer, they will take the whole thing. So let's say if they want to dope with certain ions, they will just dope the entire wafer. You agree? Now they have the equipment, you know, they will do the doping, they have different angle and things like that. So you can imagine all this doping process or etching process, you know, basically, you know, when you take the fabrication class, you know all those different steps. So basically all those processing steps, they have this location dependent factor, right? I think it's not hard to imagine, right? Imagine this is at edge of the wafer, you probably will receive a little bit different dopant compared to something in the center. Okay, so that's just reality. Of course, you know, TSMC, Global Foundry, or UMC, right? So they try really hard to have a uniform distribution. That's exactly what they are trying to do, right? In fact, you know, whichever foundry can actually achieve uniformity is gonna win most of the customer, right? So that's why you see some of foundry tend to do better than the other ones, right? Okay, but no matter how hard you try, you know, you can see that, you know, the circuit on different location of the wafer probably will behave a little bit differently. So here I'm showing you is an example. So they put, so somebody actually designed the ring oscillators. So what is a ring oscillators? So it's a bunch of inverter, right? Right? So this will oscillate. Oscillation frequency depends on the inverter delay. Do you agree? Right? So this the 3, so the period will be 6 inverter delay, right? So they measure the ring oscillators at different locations of the wafer, and then they plot the frequency. Okay, so you can see this is a megahertz. So if you go to the top, it's above 100 megahertz, and the bottom is 70-ish megahertz. So what do you see? Faster circuits tend to be in the middle of the wafer. And then if you're unlucky, you are sitting on the edge, you're a bit slower. Okay, so what do you do then, right? So if, let's say, your circuit has a requirement of, you know, hitting this frequency, then all this basically is not meeting, right? So become the trash, right? So this will be something we call as a yield, right? So that's yield matters a lot. Okay. Of course, some semiconductor company, they are smarter. They say, okay, don't call that as a trash. Don't call that as a trash. It's just a little bit slower. So what do they do? Rebrand. New line, new model. This is what I understand. You look at the Intel processor. they have what was the name? So they have a different scale, right? So I5, I7, I3, or whatever as an example. My understanding is that if you are here, I sell you more expensive, and I brand it as I7. You look at circuit, they are the same. Okay. Oh, if you are here, oh, that's I5. Are you on the edge? It's okay. You pay less, but it's still a valid product. They just run a bit slower, right? So different company has different strategy. So Intel is one of the well-known examples. I don't know about cell phone like Apple. I don't know whether they do this different grade for different cell phone. So if they do, I wouldn't be surprised. So they probably will have different scale. Okay, so that's kind of the variation, right, on the wafer level. So next I'm gonna show you some of the static errors, right, related to how we do the layout. Okay, so those will cause the variation. So here what I show you is a bunch of lines. It can be metals, right? So let's say I show 6 identical wires. And then next to it, there's a big fat wire. That's it. But when I draw it, I intend this to be 6 identical wires, right? But you know what? When you send this out to the foundry, when you get the chip back, this wire tends to be wider than this one, right? So this start to touch upon this layout effect, okay, effect. So even though when you do the layout, you say, okay, I intend to make these 6 equal weight lines, but unfortunately, just when you come back, it just won't happen. Okay. So in this case, why is this a bit wider, right? So this, by the way, anything is related to how they manufacture your chip. Okay. So in this case, oftentimes they use something called the etching, right? They will etch out. So let's say they deposit all the metal plate and they start to take out the one that you don't want. By the way, that's how they use your layout, right? The reason why they use layout, they kind of make something called a mask. You have a mask, they maybe use photons, right? They shine the light to do the pattern here, so then they know, oh, okay, this is the part you want to take it out. So you want to etch out, but guess what? Just imagine, if you have a big mountain next to you, and they want to take it out, is it easier or it's more difficult? At least that's how I naively see how they process, even though I don't understand how exactly they do it. But you can see, you have a cliff right there. So whatever that, maybe they use an ion or some chemical, go there to take it out. You see it's harder to reach that area, right? So, and it is harder to reach out to this area. That's why you see they cannot etch out as effective. As opposed to this guy, you see this pro guy, there's nothing next to it. It's wide open, right? It's wide open. So when you get edge, you probably will get edge a little bit more.
Can you just put like 2 dummy fields at the start and then?
Very good. You already kind of jump ahead. Yes. So that's why a lot of time when you do the layout, we call that I think she called that as a dummy, or basically you just want to make things kind of match left and right, right? So imagine if I have some dummy metals right there, dummy metals here, at least the center 6, which is my desired metal lines, they will be well protected. And by the way, that is very important, especially in the modern technology, right? Advanced node. That's exactly what people do, as a practice to do layout. Now, remember we have a 505 layout class. So supposedly those will be the opportunity for you to exercise. Okay, you take 505, and you can kind of go through this kind of practices, to see what will be the best layout. Okay, so basically, whatever that happened to you, next to you, will have an effect, to the circuits that you're drawing there. So that's why, sometimes, the design rule will ask you to have more spacing. Actually, that's what they do. So they will say, oh, if you want to have a thin wire and a fat wire together, they will say, okay, you know what, you should space out more. So sometimes they will just incorporate that into DRC rule. Okay, so if you do like this, they will flag the error. So okay, that's too close. Okay, so sometimes the foundry will help us to remind us, okay, this kind of proximity effect. Okay, there is something called WP effect. It's also a proximity effect, related to the whale. Okay, what whale? So in this case, it's PMOS. So PMOS, usually when we do the PMOS, right? So we put that inside the N whale, right? Because PMOS is a PMP, so your substrate is N whale, right? So you're sitting in the whale, right? So this is an N whale right here, and that's your PMOS transistor. Okay. So when you do the layout like this, how large should I circulate this N whale? By and large, if you look at this, you say, okay, so long as the PMOS is sitting inside the N whale, then you are good, right? Because I have the substrate right there. However, that's why there's something called the WP effect to tell you that you know what? It's not just you use your N whale to circle your PMOS transistors. It's also about the location of that PMOS to the edge of the N whale. Okay, so you have a distance here, you have distance here, distance here, distance there. It will affect the property of this PMOS. Okay, so here you can see there's one extreme case, right? If your PMOS is sitting here, and then this is the boundary of the N whale, let's say, usually they have a gate oxide to block this one, right? So you can see when they do the doping, right? So you can see this, maybe some ions coming from the top. I think probably even visually you can see, right? So here you can probably trap a lot more ions. It's like a valley, right? You trap all that, versus here is wide open, so it will be all spread out. So this WP effect will affect basically the property of your device. What is the property of a device? Threshold voltage, right? So that's one of them. Of course, mobility, everything else, will also affect. We use the threshold voltage, because that's usually the first order and the most dominant effect. Okay, so you're gonna see this have this variation, depends on how you draw the layout. So because of this, when we do the IC design, I know in 536A, including this class 631, we only ask you to do schematic design. I'm not gonna ask you to do a layout, right? Okay, so you design this schematic, and then there's some threshold voltage involved, and you say, oh yeah, 600 millivolt, things like that. And if you do some corner simulation, yes, it will show you some variation. Okay, depends on the process code. However, it does not capture this layout dependent effect. But who knows? Who knows when you do this PMOS, how close you're gonna put close to the N whale?
This should be taken care of in the P cell and they provide.
The P cell will only do some projection. There will some project. Yes, so he's right. So right now, the foundry give you this they call it parameterized cell. So they try to help you to pre-see, okay, what is gonna be your WP effect or some whatever proximity effect. Okay, so what they do is that they just guess. Okay, I guess that this will be the spacing to the edge. If you are super lucky, the PCL will guess exactly how you're gonna lay out. But you think about what's the probability that when you do actual layout, you're gonna do exactly the same as what PCL suggests. right? So it's probably not very high. So what you always do is that after you do the layout, you need to do so-called extraction. You need to do a post-layout extraction, then you need to simulate again, right? So think about why we are doing that. This is one of the big reasons for that proximity effect. Because a lot of times, those foundry, once you finish your layout, you're done, right? Because you say, okay, I'm gonna send this to TSMC, right, or UMC. Yeah, I know that that's your plan. And now I can help you to calculate. So they look at this and say, oh, okay, so that's actually spacing. Okay, so I'm gonna apply my model. This is gonna be your threshold voltage. This is what we call the post-layout simulation. So that's what that meant. Okay, so this post-layout extraction and resimulate is our daily job as a circuit designer. So you have to go through all this. And in fact, when you go to more advanced technology node, this has become more and more important. So I've seen cases where engineer design all the elegant circuits in schematic. He was so happy. Look, it's a tough spec. I meet everything. After you do layout, extract, everything screw up. Even the biasing point is not working.
Assume that we are not that concerned with circuit area. Can we do? Will it be meaningful to do like isolated and well for each PMOS, or is that just?
You can do that. Yes, actually, yeah. If you are not that constrained, you can play safe. So you can say that, okay, you know what? Let me just open up this, and this was sitting right in the middle. So you can see you will get less affected by this edge impact. Yes. So you absolutely can do that. But you also point out it's basically the trade-off between how much area you're gonna burn. You guys all understand how expensive the advanced node is, right? So you're paying, yeah, is it one mask is $1 million or something like that, so or multi-million dollars. So now it's so expensive, you're paying tons and tons of money to this. Okay, so good luck with that. Talk to your manager. Yeah, I learned from Mike's class, there's something called WP effect. Yeah, I'm gonna have this and just put one PMOS transistor. Yeah, so good luck with that. And then they will say, okay, yeah, how much money you're costing our company? Yeah. Okay, so that's gonna be the real life that you guys gonna have fun with, right, in the future. If you are in the older technology node, remember last time I talked about different technology nodes, right? If you are in the older technology, generally speaking, this type of impact will be less. Okay, I think intuitively, I think that kind of makes sense, right? If you think about why our transistor now can be so compact, so small, right? So that pretty much suggests that all the process engineer, they leverage everything they possibly can. They squeeze everything to the final limit. There's no room. There's no margin. Okay, so if you shift a little bit here and there, you probably will screw up, whatever the intended effect, right? So all this impact in general, it become more and more serious. Of course, the foundry know about this. That's why he mentioned about the P cell, right? The parameter cell. So let's say they have a P cell on the PMOS, right? So they will try their best to incorporate this, they call it the layout effect. All this pre-layout effect, they already include in the model, right? To kind of predict this is gonna be the anticipated final threshold voltage or mobility and things like that, right? But there's so much that they can do. And the answer really about whether your final layout will be exactly the same as what the model predicts. Right? So if that's not, then it is not. Okay, so unfortunately you're gonna spend a lot of time to do not just the layout, but also after layout you're gonna redesign your circuits. Okay. So sometimes what people do is that when they design the circuit, they will leave some margin for that reason, right? So it's, oh yeah, what if this threshold voltage is gonna be plus minus 100 millivolts? Okay, so that means what? That means your VD set probably will change plus minus 100 millivolts, right? Remember how, so let's say if you wanna keep the transistor in the saturation region, what do you do? Your VDS? Larger than VD set, right? Imagine if you design your circuit just right at the VD set, plus minus 100 millivolts, you're off. So you got to leave some margin, right? So in this case, even if you make the VDS a little bit higher, that will help. Okay. So that's WP effect related to the layout. Temperature. We talk about temperature can change, over seconds or minutes, right? That kind of time scale. But you know what? The temperature can also vary based on the location. So this is a real thermal image. Okay, so when they operate the circuit, they do a thermal image. You can see here, this temperature is 1.5 degrees C higher than the rest, right? Within 0 degrees. Why is that hotter there?
More devices.
More devices,
Active, like,
more
active, like uses
more action going on, right? Right, because you may also have millions of devices there, but if they are off, nothing there. Okay, so this is really a map to see which part of your circuits are actively working, right? So these are ADC, but you can imagine even for CPU, GPU, they are the same. If some of the core you're operating, so that will be hotter than the best. And by the way, because of this, that's why they want to put the temperature sensor for each core, for that reason. Actually, have you guys, on your laptop, I don't know about your laptop, but my laptop, I can do some self-diagnosis.
Yeah.
Or have you guys tried that? Because my laptop has some issue a couple months ago. So I want the company to help me to fix. They said, no, you need to run a self-diagnosis. Right? And I go, what is that? So they told me, okay, run this tool. And then they show me, okay, all my CPU core. By the way, that's how I knew. All my CPU core, this core number 1, that's the temperature. Core number 2, temperature. And by the way, they plot the temperature over time. Say no, so I remember maybe I have 20 cores. Okay, so 20 cores, each core temperature over time, plot that. And they say, okay, Mike, we want to see whether that's go over 90 degrees C, something like that. And it did actually. So they said, okay, yeah, we're gonna replace your CPU. So they actually monitor all this, even for debugging purpose. Okay, so that's that. So debugging is one good example, right? That's my personal experience. Sometimes, actually also related to my personal experience. Sometimes you can use this temperature monitoring, right? The thermal image to do the debugging, right? So remember I told you about these days the leakage current is so important. Because when you are in the sleep mode, you want your circuit to be asleep. Don't wake up. Really sleep, you consume no current. How would this be helpful? So, assuming if I am in the power down mode, nothing leak. If you look at thermal image, you should see everything's dark. What if there's a shiny star lit up right there? What happened? It gotta be some current leaking there. And you know what? The next step is that they say, okay, yeah, in this location, who designed this block? I knew that because I did that before. So there was one of the products, I need to check exactly debugging this leakage current. And we're trying to see, because everybody said, do you put the power down? We asked all the designers in the team. Everybody said, yeah, I did. What do you mean? I spent the whole month, making sure I run the simulation, everything is working, right? Everybody said that they did it. Fine, let's do thermal image. We do thermal image, we found, okay, that designers, which I won't name who that person was, but it's not very fun, right? So they would look at this and they, okay, that designer, screw up. Okay, so all this are actually quite helpful. STI stress, again, this is related to the mechanical. So basically, when you have a device, right? So you may have some trench on the side to do the isolation, but because it's all physical object, right? So you can imagine, there will be some, force, right? So you may have some force, like somebody squeezing you, right? So you actually have some mechanical force, and unfortunately, all this mechanical force, it will change the actual electrical property. In this case, it's mobility, right? So your mobility can actually change. Okay, so if that's a tensile stress, it will increase the mobility. If that's compressed, it will increase the whole mobility. Okay, so your mobility, the mu factor, remember the mu factors, it will affect, depends on, how much stress you are receiving. Okay, so people actually, measure this, right? So let's say this is a transistor, right? So this is the gate, and you have the trench on the side. So you can see that, because when you are closer to the edge, you receive more stress, mechanical stress. And when you're in the middle, you have the less stress. So this is a stress pattern. You see this stress pattern over the location of your transistors. Okay, and because all these are having different mobility, right? Unless you are really in the middle. You see all this middle, you receive roughly the same stress. Okay, so what should I do when I do the layout? Let's still go back to the dummy, right? So usually what you want to do is that, let's say you have all these transistors, right? So these 2 transistors or 3 transistors, right? So all this. Usually you would at least put 1, or maybe sometimes 2, sometimes 3, so it depends on your patterns. So this is what we call the dummy, right? So this transistor is actually not used, but you just repeat, that's why they call dummy, right? Dummy transistors, very common. This is a common practice. So you have to put the dummy transistor on the side, so that you see when you have this non-uniform stress, right? It will be on the edge. Who cares? I'm not gonna use it, anyways. And whatever that in the middle are the good one. So they will be closer to my model. They will match to each other better, right? So this is very important. Okay. So as a result, the foundry, what they characterize is they call it the LOD effect. So basically the diffusion depth, right? So this is a drain and source. So this is a gate, this is a drain and source, right? So you have a stress on the side. You have this, and they characterize different distance. Okay, so different width on this, or different depth of this drain and source diffusion area. So that's why they call it length of diffusion. So they characterize, what's the impact, for the beta, right? So there's mobility and also the threshold voltage, right? So it will actually affect, depends on the location, right? So let me just give you an example. So let's say if I want to do 4 transistors right here, right? By the way, you still remember this layout? I think I talked about this in 536A, right? So here, let's say I have 4 different transistors. A, B, C, D. What is the LOD of the transistor A? So you see, transistor A to the left, the length of diffusion is this, right? To the right, this. What about transistor B? What's the LOD to the left? So you have this, and you have this. If I want to do a good matching between A and B, does it match? It does not match. On the layout, you look and say, okay, Mike, how is this fair? I draw them exactly the same. right? You teach us that 5, this is 8, yeah, this is 4 identical transistors. Drain source, right? But then you see just the LOD effect, they are different, right? They are different. Would adding dummy help in this case? So let's say this ABCD are the desired transistors. So if I add 2 more here, 2 more there,
No.
You're still changing the V's.
yeah. So it won't be identical. However, it can be better. Why is that? Because you see, this distance will be longer. Everybody, the distance will be longer. So the ratio between those can be a little bit closer. Okay. No matter how you look at it, that's why for the analog, especially sensitive analog circuit design, adding those dummies on the side, always helpful. Okay. Now, so if you in the future work on the very advanced nodes, especially like FinFET, my impression is that actually people do tons and tons of dummies, a lot of dummies, right? Sometimes even 4, 8, or even more, right? So that's if you do care about this. So my suggestion is that you just do post layout simulation. Try it out. Insert 2 dummies, 4 dummies, 8 dummies, 16 dummies, until to the point where you say, oh, okay, there's no difference. Or they match very closely. Then you know that's where you should stop. Okay. And of course, you know, the money is still an issue, right? So the more dummy, that means you waste more area. So you still need to discuss with your manager to make sure that is okay. Okay, any question? If not, let's take a short break.